October 21st, 1943. 8 miles east of Salerno, Italy, the Sorrento Peninsula. Corporal Michael "Mike" Donovan sits in the driver's seat of his M4 Sherman tank, Iron Horse, staring up at a slope that shouldn't exist on any road map. The angle is impossible, 45 degrees, maybe 50. A narrow mountain road carved into volcanic rock, switchbacking up toward German positions dug into the hills above the Amalfi coast. His platoon leader, Lieutenant Robert Hayes, stands outside the tank, binoculars raised, studying the climb. The German 105th Panzer Grenadier Division holds the high ground. They've turned every ridge into a fortress. The only way forward is up, straight up. Hayes lowers his binoculars and walks over to Iron Horse. "Donovan, we need to get up that road. Intelligence says it's the only approach that won't put us in range of their 88s until we're practically on top of them." Donovan leans out of his hatch, looks up at the slope, feels his stomach tighten. "Sir, that's got to be 45 degrees, maybe more at the switchbacks. Closer to 50 in places. Sir, the manual says Shermans can handle 30-degree grades, maximum, maybe 35 if the surface is good and we're not loaded." "We're loaded. 30 tons. Full combat load. Ammunition, fuel, crew, everything." Donovan does the math in his head. Weight distribution on a slope that's steep means the center of gravity shifts backward. The front of the tank goes light. The tracks at the front lose traction. The engine has to overcome not just rolling resistance, but gravity pulling 30 tons downhill. The transmission has to transfer 500 horsepower through a clutch system designed for relatively flat terrain. "Sir, if we lose traction halfway up, we roll backward." "I know, but the infantry can't take those positions without armor support. The Germans have machine gun nests covering every approach. We either get tanks up there, or our boys die trying to advance without us." Donovan looks at his crew. His bow gunner, Private Tommy Rizzo, 20 years old, from Brooklyn. His gunner, Sergeant Frank Chen, 24, San Francisco. His loader, Private First Class Eddie Walsh, 19, Boston. His assistant driver, Private Carl Hendricks, 22, Des Moines. All of them looking at him, waiting. "Sir, I can try, but if the clutch slips, then we deal with it. Mount up." What Donovan doesn't know is that his concern isn't just theoretical, it's a pattern, and it's killing crews across the Italian theatre. Between September 15th and October 20th, 1943, the Fifth Army reports 27 Sherman tanks disabled during attempts to climb steep grades in the mountains north of Salerno. Not destroyed by enemy fire, disabled by mechanical failure, specifically clutch failure. The clutch assembly that transfers power from the engine to the transmission burns out under the strain of steep climbs. When the clutch fails, the tank loses power. On a steep slope, that means rolling backward, out of control. 30 tons of steel and ammunition tumbling down a mountainside. 14 tank crews, 70 men, have been killed or seriously injured in rollback accidents in the past 5 weeks. That's more crew casualties than the division has suffered from German anti-tank fire in the same period. The problem isn't the engine. The Ford GAA Vate produces 500 horsepower, more than enough power to climb steep grades. The problem is the clutch. The dry disc clutch system that connects the engine to the transmission wasn't designed for sustained high-torque, low-speed operation on extreme grades. Under normal conditions, the clutch works perfectly. Flat terrain, rolling hills, even moderate slopes up to 30 degrees. The clutch engages smoothly, transfers power efficiently, runs cool, but on slopes exceeding 40 degrees, everything changes. The driver has to maintain high engine RPM to generate enough power to overcome gravity. Simultaneously, the transmission needs to stay in first gear, sometimes second, to maintain torque. This creates a mismatch: high engine speed, low transmission speed, massive torque load. The clutch, caught between a screaming engine and a labouring transmission, begins to slip. The friction material heats up 600 degrees, 700, 800. At 900 degrees, the organic friction material begins to break down. At 1000 degrees, it fails completely. The clutch disc glazes over. Friction drops to near zero. Power transmission stops. The tank dies on the slope. If the crew is lucky, they can engage the parking brake before momentum carries them backward. If they're unlucky, the brake can't hold 30 tons on a 50-degree slope. The tank rolls. Back at the ordnance depot in Naples, engineers know about the problem. They've known since late September. Field reports from the DAR, 36th Infantry Division describe multiple clutch failures during mountain operations. The recommended solution is clear. Replace the organic friction clutch disc with a sintered metal disc. Sintered metal can handle temperatures up to 1500 degrees without significant degradation. Problem solved. Except production of sintered metal clutch discs requires specialized manufacturing equipment. The discs are made by compressing metal powder under extreme pressure, then heating it until the particles fuse. Only 3 factories in the United States have the equipment. Current production is allocated entirely to aircraft applications. Aircraft clutches, propeller governors, high-performance brake systems. The military aviation program has priority. Tanks have to wait. Estimated timeline for sintered metal clutch availability, March 1944. That's 5 months away. The Italian campaign cannot wait 5 months. The Fifth Army is advancing now. German positions are in the mountains now. Tank crews are dying now. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. On October 8, 1943, Army Ordnance issues a technical bulletin. Sherman tank operations on grades exceeding 35 degrees are not recommended due to clutch thermal limitations. Tank commanders should seek alternate routes when possible. Avoid sustained high-torque, low-speed operation. Monitor clutch temperature if gauge is available. Most Shermans don't have clutch temperature gauges. Tank commanders in Italy respond with frustration. Seek alternate routes. In the Italian mountains, there are no alternate routes. The roads go where they go. The Germans hold the high ground. American forces have to climb to get to them. Avoiding steep grades means avoiding combat. That's not an option. Lieutenant Colonel William Morrison, commanding officer of the 67th Armored Regiment, writes a memo to 5th Army Headquarters on October 10th. Clutch limitations on Sherman tanks severely restrict operational capability in mountainous terrain. Enemy forces exploit this limitation by occupying positions accessible only via steep grades. Our armor cannot support infantry assaults on these positions. We require either improved clutch systems or alternative tactical approaches. Current restrictions unacceptable. The response from headquarters is bureaucratically sympathetic but operationally useless. Ordnance Department is aware of clutch limitations. Improved components are in development. Estimated availability, Spring 1944. Until improved components become available, tactical planning should account for Sherman mechanical limitations. Translation: learn to fight without tanks in the mountains, or wait until spring. Neither option is acceptable. But 600 miles north, in a maintenance depot outside Naples, a 38-year-old mechanic with grease under his fingernails is about to prove that Army Ordnance doesn't know everything about clutches. Raymond Ray Sullivan doesn't have an engineering degree. He has a 10th grade education and 22 years of experience working on farm equipment, construction machinery, and trucks. Born in Bakersfield, California in 1905, Ray grew up on a cotton farm during the Depression. His family couldn't afford a new tractor, so they bought used equipment, and Ray learned to keep it running. By 16, he could rebuild a clutch blindfolded. By 20, he was working as a traveling mechanic, servicing agricultural equipment across the San Joaquin Valley. When the war started, Chrysler hired him to work at the Detroit Tank Arsenal. His supervisor's evaluation from January 1943 reads, Sullivan, R. Mechanic, Powertrain Section, excellent diagnostic skills, efficient repairs. Limited formal education may restrict. Advancement to supervisory roles. Recommend continuation in current technical capacity. Nobody expects innovation from a farm mechanic who fixes clutches. But Ray notices things. Specifically, he notices the pattern in clutch failures. Every week, damaged Shermans arrive at the depot. Combat damage, track failures, transmission problems, and increasingly, clutch failures. Ray is assigned to the clutch replacement team. His job is simple: remove the failed clutch assembly, install a new one, test it, send the tank back to the front. He's done this repair hundreds of times. Pull the transmission access plate, disconnect the clutch linkage, unbolt the pressure plate, slide out the clutch disc, inspect for damage. The pattern is consistent. The friction material on the disc is burned, glazed smooth, sometimes cracked, sometimes completely disintegrated, leaving only the metal backing plate. October 14th, 1943. Ray is rebuilding the clutch on a Sherman that rolled backward down a mountainside near Avellino. The tank commander and driver were killed in the accident. The rest of the crew survived with injuries. The clutch disc is completely destroyed. The friction material has burned away entirely. What's left is a bare metal disc, useless. Ray tosses the ruined disc into the scrap bin, the same bin where dozens of identical failures have accumulated over the past month. Then he pauses, picks up the disc, examines it carefully. The friction material is gone, but the metal backing plate is intact. The splines that connect to the transmission input shaft are undamaged. The hub assembly is fine. The only failure is the friction material itself. Ray thinks about the problem. Organic friction material can't handle the heat. That's established. Sintered metal can handle the heat, but it's not available. So, the question becomes, what material is available that can handle heat better than organic friction material, but doesn't require specialized manufacturing? He walks over to the spare parts section, looking for inspiration. Passes shelves of track links, sprockets, road wheels, transmission gears, stops at a bin of brake linings. Sherman tanks use steel brake drums with woven asbestos brake linings. Asbestos is heat-resistant. That's why it's used in brakes. Brake systems routinely handle temperatures exceeding 1,000 degrees. Ray picks up a brake lining. It's flexible, woven asbestos fibers bonded with phenolic resin, attached to a metal backing plate with rivets. The friction characteristics are different from clutch material, but the heat resistance is superior. Ray does some quick mental calculations. A clutch disc is approximately 10 inches in diameter. A brake lining is approximately 14 inches long and 3 inches wide. If you cut the brake lining into strips and rivet them to a clutch disc backing plate, you'd have a heat-resistant friction surface. It's a crude idea. Brakes and clutches operate on the same principle, friction, but they're designed for different applications. Brakes need to create maximum friction to stop rotation. Clutches need to create controlled friction to transfer power smoothly. Using brake material in a clutch could work, or it could create a clutch that either slips constantly or engages too aggressively. There's only one way to find out. October 15th, 1943. Ray takes a failed clutch disc and a salvaged brake lining to his workbench. He's working during his lunch break, unauthorized, using scrap materials. If this works, he'll report it. If it doesn't work, nobody needs to know he tried. He measures the clutch disc carefully, 10¼ inches in diameter. The original friction material covered the outer 8 inches, leaving the center 2 inches for the hub assembly. He needs enough brake lining material to replicate that coverage. Ray cuts the brake lining into strips. Each strip is 2 inches wide, 6 inches long. He'll need 16 strips to cover the surface area of both sides of the clutch disc. The cutting is tedious. The asbestos fibers are tough, resistant to his hacksaw. He switches to aviation snips, cutting slowly to avoid fraying the edges. By the end of his lunch break, he has 16 strips of brake lining material. He positions them on the clutch disc backing plate, arranging them in a circular pattern. The fit isn't perfect. There are gaps between strips. The coverage is uneven, but it's close enough for a test. Now comes the hard part: attachment. The original friction material was bonded to the backing plate with high-temperature adhesive. Ray doesn't have that adhesive. What he has is rivets. Lots of rivets. Sherman brake linings are riveted to their backing plates. The same technique should work for a clutch disc. Ray drills holes through the brake lining strips and through the clutch disc backing plate. 16 strips, 4 rivets per strip, 64 holes total. He uses a hand drill. The work is slow, precise. Each hole must be positioned carefully to avoid weakening the backing plate. By 1800 hours, he's finished drilling. He installs the rivets, one by one, using a pneumatic rivet gun. Each rivet is carefully set, flush with the surface of the brake lining material. The finished product looks rough. The brake lining strips are slightly uneven. The rivet heads are visible, creating small bumps in the friction surface. It's not pretty. It's not precision engineering, but it's heat-resistant. Ray weighs the modified clutch disc in his hands. It's heavier than the original. The brake lining material is denser than organic friction material, approximately 3 pounds heavier. That extra weight will increase rotational inertia slightly, which could affect engagement characteristics, or it could make no difference at all. He needs to test it. October 16th, 1943. Ray arrives at the depot before dawn. He's going to install his modified clutch disc in a Sherman and test it before anyone notices. The tank he selects is an M4 A1, call sign Desert Fox, recently repaired after throwing a track during maneuvers. The clutch is functional, standard organic friction disc, but Ray replaces it anyway with his brake lining modification. The installation takes 90 minutes. Disconnect the clutch linkage, remove the transmission access plate, unbolt the pressure plate, slide out the standard clutch disc, slide in the modified disc, reinstall everything in reverse order. By 07:30 hours, Desert Fox is ready to test. Ray climbs into the driver's seat, starts the Ford GAA engine. It rumbles to life, settling into its characteristic vait idle. He lets it warm up for 5 minutes, watching the gauges. Oil pressure good, coolant temperature rising normally, everything nominal. He presses the clutch pedal. It moves smoothly, normal resistance. He shifts into first gear. The shift is clean. No, grinding. So far, so good. He releases the clutch pedal slowly. This is the critical moment. If the brake lining material has too much friction, the clutch will engage too aggressively. The tank will lurch forward, possibly stalling the engine. If the material has too little friction, the clutch will slip. The engine will rev, but the tank won't move. The clutch engages at about the same pedal position as a standard clutch. The engagement is slightly more abrupt, a bit less smooth, but acceptable. The tank moves forward. Ray accelerates gently, shifts into second gear, then third. The clutch operates normally. He drives Desert Fox around the depot yard for 10 minutes, testing starts, stops, shifts. Everything works. The modified clutch disc functions as a clutch. But the real test isn't normal driving. The real test is heat. Ray needs to simulate the conditions that destroy standard clutches: high engine RPM, low gear, sustained load. He finds a section of the depot yard with a moderate slope, maybe 15 degrees. He drives Desert Fox to the bottom of the slope, shifts into first gear, and advances up the slope at high engine speed. The engine screams at 3,500 RPM. The transmission is in first gear, maximum torque multiplication. The clutch is under heavy load, transferring 500 horsepower through friction. Ray holds this condition for 2 minutes. On a standard clutch disc, this would generate enough heat to cause slippage. With the brake lining material, the clutch holds. No slipping, no loss of power. The tank climbs the slope steadily. Ray stops halfway up the slope, engages the parking brake, and shuts down the engine. He climbs out of the tank, opens the transmission access plate, and carefully touches the clutch pressure plate. It's hot, very hot. too hot to hold his hand against for more than a second, but the clutch didn't fail. Ray lets the assembly cool for 15 minutes, then restarts the engine and completes the climb. The clutch still works. He drives back down the slope, testing the brakes. The brake lining material in the clutch doesn't seem to have affected brake performance. Both systems operate independently. Ray returns to the maintenance bay and removes the modified clutch disc for inspection. The brake lining material shows slight discoloration from heat, but no cracking, no glazing, no material breakdown. The rivets are intact. The friction surface is still functional. The modification survived a test that would have damaged a standard organic friction disc. Ray knows he's onto something, but he also knows that a 15-degree slope for 2 minutes isn't the same as a 50-degree slope for 20 minutes. He needs a more demanding test. He needs a real mountain, and he needs someone willing to risk their tank on an unauthorized modification. October 17th, 1943, Maintenance Depot, Naples. Technical Sergeant Howard Mitchell is Ray's immediate supervisor. Mitchell is 42 years old, career Army, enlisted in 1921, served in the Philippines, Hawaii, and now Italy. He's seen enough equipment failures to respect mechanics who think creatively. Ray approaches him after morning formation. Sergeant Mitchell, I need to talk to you about clutch failures. Everybody needs to talk to me about clutch failures. We're replacing 6 to 8 per week. What about them? I think I can fix the problem. Mitchell looks at him skeptically. Army ordnance says sintered metal clutches are the fix. They're not available until spring. I'm not talking about sintered metal. I'm talking about brake lining material. Ray explains his modification. Mitchell listens without interrupting. When Ray finishes, Mitchell asks the obvious question. Did you test this? Yes, Sergeant. Installed it in Desert Fox yesterday. Drove it around the yard, tested it on the slope behind the motor pool. Clutch operated normally. No slipping, no failures. That's not a mountain. No, Sergeant. That's why I need permission to test it on a real climb. Something steep enough to stress the clutch the way combat operations would. Mitchell thinks for a long moment. He's thinking about regulations, about unauthorized modifications to Army equipment, about what happens if the modification fails and a crew gets hurt. He's also thinking about 14 dead tankers in the past 5 weeks, men who died because their clutches failed on mountain slopes. You understand if this fails, if the clutch gives out halfway up a mountain and the tank rolls backward, that's on you. Court-martial, Leavenworth, dishonorable discharge. Yes, Sergeant. And you still want to test it? Sergeant, we're losing crews to clutch failures every week. If this works, we stop losing them. If it doesn't work, I take the blame. But we have to try. Mitchell walks over to the window, looks out at the depot yard. Dozens of Shermans in various states of repair, some damaged by enemy fire, more damaged by terrain and mechanical failures. He's spent 22 years in the Army. Most of that time he's followed orders, filed paperwork, maintained equipment according to regulations. But sometimes regulations don't save lives. Sometimes taking a risk does. He turns back to Ray. There's a test route the Italians used before the war. Strada di Montagna, mountain road, runs from the valley floor up to a village called Ravello. Approximately 6 miles of switchbacks. Some sections hit 45 degrees, maybe 50. The Germans abandoned it because their supply trucks couldn't make the climb. Too steep. That sounds perfect. It's also exposed. German observation posts can see it from the high ground. If they spot a Sherman on that road, they'll call artillery. We'll test at night. Mitchell nods slowly. You'll need a crew. Volunteers only. Nobody gets ordered to test an unauthorized modification. I'll ask Lieutenant Hayes. His platoon has been requesting tanks that can handle mountains. Hayes is aggressive. Maybe too aggressive. But if anyone will volunteer for this, it's him. October 18th, 1943. Forward staging area, 3rd Battalion, 67th Armoured Regiment. Lieutenant Hayes stands beside Iron Horse, studying a topographical map of the Sorrento Peninsula. Ray Sullivan and Sergeant Mitchell approach. Hayes looks up, recognizes Mitchell, nods. Sergeant Mitchell, what brings maintenance up to the line? Lieutenant, we may have a solution to your clutch problem. Hayes's expression shifts from casual interest to intense focus. I'm listening. Ray explains the modification. Hayes listens, asks technical questions. The brake lining material, it can handle sustained high temperature? Tested it on a moderate slope. Clutch held without slipping, no material degradation. Moderate slope isn't Strada di Montagna. No, sir. That's why we need a field test. Real combat conditions, steep grades, sustained load. Hayes folds his map. You're asking me to take my tank up a mountain road using an untested modification? Yes, sir. If the clutch fails halfway up, we roll backward. Yes, sir. Could kill my crew. Yes, sir. Or it could save your crew and every other crew that needs to operate in mountains. Hayes looks at his tank, at his crew working nearby. Donovan is checking the tracks. Rizzo is cleaning the bow machine gun. Chen is inventorying ammunition. Walsh is securing fuel cans. Hendricks is refilling water containers. They're young. The oldest is 24. They trust him to bring them home alive, taking them up an exposed mountain road at night in a tank with a modified clutch. That's asking a lot. But so is watching other crews die because their clutches fail on slopes they have to climb. When do you want to test? Tonight, sir. 2200 hours. Minimal visibility reduces German observation. What do you need from me? Your tank, your crew, and approximately 3 hours. Hayes walks over to his crew. Gather round. The 5 men assemble. Hayes explains the situation clearly. The clutch problem, Ray's modification, the test, the risks. He doesn't sugarcoat anything. If the clutch fails on Strada di Montagna, they could die. But if the modification works, it could save hundreds of crews across the theatre. Donovan speaks first. Sir, I've been driving Shermans for 8 months. Lost 2 tanks to mechanical failures. Never lost one to German fire. If there's a chance this modification improves reliability, I'll test it. The rest of the crew nods agreement. Rizzo adds, we're going to climb those mountains one way or another. Might as well do it with a clutch that works. Hayes turns back to Ray and Mitchell. We're in. Install your modification. We test at 2200. The next 4 hours pass in focused activity. Ray and Mitchell remove Iron Horse's standard clutch, disc and install a modified disc with brake lining material. The installation is careful, methodical, every bolt torqued to specification, every connection checked twice. By 2000 hours, the modification is complete. Ray test drives the tank around the staging area. The clutch operates normally. Smooth engagement, no slipping, proper power transfer. At 21:45 hours, Hayes and his crew mount up. Donovan starts the engine. The Ford GAA rumbles in the darkness. No lights. They'll navigate by moonlight and familiarity with the terrain. Mitchell and Ray climb aboard a jeep to follow at a safe distance. If Iron Horse rolls backward, the jeep crew can call for recovery. If the Germans spot them, the jeep can provide suppressing fire while the tank retreats. Neither outcome is ideal. At 2200 hours, Iron Horse reaches the base of Strada di Montagna. The road is barely visible in the moonlight, narrow, steep, carved into the mountainside. The first, switchback, is 300 yards ahead, climbing at approximately 40 degrees. Donovan shifts into first gear, advances slowly. The tank's tracks bite into the dirt and gravel surface. The climb begins. The Sherman's nose tilts upward. The angle feels impossible, like climbing a wall. Donovan maintains steady throttle, keeping engine RPM at 3000. The transmission is in first gear, Maximum torque multiplication. The clutch is under extreme load. This is the condition that destroys standard clutches. High engine speed, low transmission speed, massive torque transfer. The tank climbs. 50 yards, 100 yards, 150 yards. The clutch holds. No slipping, no power loss. Donovan can feel the difference. On previous climbs with standard clutches, he'd feel the slight hesitation as the clutch began to slip. The brief moment where engine speed increased but tank speed didn't. That hesitation isn't happening. Power transfer is solid, consistent. 200 yards. 250 yards. The first switchback is ahead. Donovan slows slightly, turns hard right. The tracks dig into loose gravel. The outside track lifts slightly as weight shifts to the inside. This is a critical moment. If traction fails, the tank could slide sideways off the road, but the tracks hold. The turn completes. Iron Horse is pointed up the next section of the climb. This section is steeper, 45 degrees, maybe 48. The tank's nose points almost straight up. Inside the hull, Chen braces himself against the gun mount. Walsh holds onto the turret traverse handle. Rizzo presses his feet against the bow gunner's footrests. The angle is severe enough that loose equipment slides backward. A wrench clatters down the floor, comes to rest against the engine compartment bulkhead. Donovan keeps his right foot steady on the accelerator. The engine screams. The clutch transfers 500 horsepower through friction material that should be failing by now. But it doesn't fail. The brake lining material handles the heat, maintains friction coefficient, keeps the tank moving upward. 300 yards, 400 yards, 500 yards. They're halfway to the first ridge. Behind them, Mitchell and Ray follow in the jeep, stopping frequently to avoid getting too close. If Iron Horse loses traction and rolls backward, the jeep needs time to get out of the way. 600 yards. The second switchback appears ahead. This one is tighter, sharper, carved around a rocky outcrop. Donovan slows to a crawl, almost stopping. He turns hard left. The tracks scrape against rock. Metal squeals against stone. The turn is so tight that the tank almost can't make it. The outside track climbs onto a boulder, lifting the left side of the tank 2 feet higher than the right. For a moment, Iron Horse balances on 3 track assemblies and 1 boulder. Hayes, standing in the turret, feels the tank tilt. He grabs the turret edge, ready to order evacuation if the tank goes over. But Donovan gives it more throttle. The tracks dig in. The tank crawls over the boulder and completes the turn. They're through the switchback, pointed up the next section. This section is the steepest yet, 50 degrees. The manual says this is impossible. The manual says Shermans cannot climb slopes exceeding 35 degrees for sustained periods. But Iron Horse is climbing 50 degrees, and the clutch is still holding. 700 yards, 800 yards, 900 yards. The ridge is close. Donovan can see the crest ahead, silhouetted against the night sky. One more push, one more section of impossible grade. The engine is howling at maximum RPM. The transmission is in first gear, gears meshing under tremendous load. The clutch is transferring all of it, friction material, maintaining grip despite temperatures that must be exceeding 1,000 degrees. 1,000 yards, 1,100 yards. The grade begins to level off, 40 degrees. 35 degrees, 30 degrees. Iron Horse crests the ridge and rolls onto relatively flat ground. Donovan releases the accelerator, lets the engine drop to idle. He engages the parking brake and shuts down the engine. The silence is profound. For 3 minutes, all they've heard is screaming engine and clattering tracks. Now, nothing. Just wind and the distant sound of artillery fire from German positions further north. Hayes climbs out of the turret, jumps down to the ground. Mitchell and Ray arrive in the jeep moments later. Hayes walks over to them, his expression unreadable in the darkness. Then he grins. That clutch just climbed a 50-degree slope without slipping once. Not once. I felt it the whole way. Solid power transfer, no hesitation. Ray and Mitchell approach Iron Horse. Ray opens the transmission access plate, shines a flashlight inside. The clutch assembly is glowing dull red, visible heat radiating from the metal. He lets it cool for 10 minutes, then carefully touches the pressure plate with a gloved hand. Still hot, but not dangerously so. "We need to inspect the friction material," Ray says. He begins the disassembly process right there on the mountain ridge. Hayes provides light, while Ray removes the clutch assembly. The process takes 30 minutes. When Ray finally slides the clutch disc out and examines it under flashlight, he sees what he hoped to see and feared he wouldn't. The brake lining material is discolored, darkened by heat, but it's intact. No cracking, no glazing, no material separation from the backing plate. The rivets are tight. The friction surface shows wear, but normal wear, the kind that happens gradually over hundreds of hours of operation, not catastrophic wear that happens in minutes. "It worked," Ray says quietly. "The modification worked." Mitchell examines the disc himself, running his fingers over the friction surface. This climbed 50 degrees for nearly half a mile. A standard clutch, it would be destroyed. Hayes looks at both men. "How fast can you make more of these?" "Depends on materials and manpower," Ray replies. "The limiting factor is riveting the brake lining to the clutch discs. Each disc requires 64 rivets, installed precisely. With one man working, maybe one disc per day. With more help, faster." "How many tanks in the battalion need this?" "All of them, sir. Every Sherman operating in mountainous terrain needs better clutch heat resistance." Hayes makes his decision. "Sergeant Mitchell, I'm formally requesting that maintenance retrofit my entire company with this modification." 32 tanks. How long?" Mitchell does the math. "With adequate manpower, 2 weeks. Maybe less if we work around the clock." "You have 1 week. We're advancing up the Sorrento coast, starting October 26th. I need my tanks able to climb." If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. October 19th through October 25th, 1943. The maintenance depot becomes a clutch modification production facility. Ray trains 8 other mechanics in the process. They develop an assembly line. Station 1, disassembly. Remove standard clutch discs from tanks. Station 2, preparation. Clean and inspect the backing plates. Station 3, cutting. Cut brake lining material into strips using aviation snips and templates. Station 4, drilling. Drill rivet holes through both the brake lining and backing plates. Station 5, riveting. Install 64 rivets per disc using pneumatic rivet guns. Station 6, quality control. Inspect each completed disc for proper rivet tension and material alignment. The process is repetitive, tedious, but effective. Each mechanic completes approximately 2 discs per 8-hour shift. With 9 mechanics working 3 shifts per day, they produce 54 discs per day, enough for 27 complete tanks in the first 3 days. By October 22nd, they've modified 43 tanks. By October 24th, 62 tanks. By October 25th, 81 tanks. They're ahead of schedule. The modification is spreading beyond Hayes's company. Other tank commanders hear about the test on Strada di Montagna. They request the modification for their tanks. Mitchell approves every request. No authorization from higher headquarters. No approval from Army Ordnance. Just mechanics installing better clutches because better clutches keep crews alive. Captain Robert Greer, the battalion maintenance officer, notices the activity on October 23rd. He walks into the workshop, sees 8 mechanics simultaneously riveting brake lining material to clutch discs, asks Mitchell what's happening. Mitchell explains everything. The clutch failures, Ray's modification, the successful test, the production line. He doesn't apologize. He doesn't make excuses. He just states facts. Greer listens, then asks to see a completed disc. Mitchell hands him one. Greer examines it carefully. The riveting is precise. The material coverage is good. The workmanship is solid. He looks up at Mitchell. This is field modification of Army equipment without authorization. Yes, sir. Did you test it? Yes, sir. Lieutenant Hayes took it up Strada di Montagna. 50-degree slopes. Clutch performed perfectly. One test. 81 tanks now have this modification, sir. They've been operating for the past week. 0 clutch failures reported. Greer hands the disc back to Mitchell. Thinks for a long moment. He's 36 years old, commissioned through ROTC in 1931. He's been in Italy for 4 months, long enough to see how many crews die from mechanical failures versus enemy action. Long enough to know that sometimes the regulations exist to prevent problems that matter less than the problems they create. I didn't see this, Greer says finally. I don't know anything about modified clutches. If Army Ordnance asks, you developed this on your own initiative to address an urgent operational requirement. You used salvaged materials and existing tools, so there's no requisition trail. No paperwork, no formal approval, no evidence except tanks that don't break down anymore. Understood, sir. How many more tanks need this modification? Approximately 200 in the division, sir. You have 2 weeks. After that, we're advancing north, and I need every tank operational. October 26th, 1943. 0600 hours. The 67th Armoured Regiment begins its advance up the Sorrento coast. 43 Shermans with modified clutches form the lead elements. The terrain is exactly what everyone feared. Steep mountain roads, switchbacks, grades exceeding 40 degrees in multiple locations. German positions on the high ground, dug into rock, nearly impossible to assault without armour. Support. Lieutenant Hayes's platoon takes point. Iron Horse leads, Donovan driving, the modified clutch performing exactly as it did during the test climb. Behind Iron Horse, 4 more Shermans follow, all with modified clutches, all climbing grades that should be impossible. The German defenders watch in confusion. Their intelligence assessments, based on earlier American operations, predicted that American armour would be restricted to valley floors and moderate slopes. The steep approaches to their positions were supposed to be tank-proof, but the Americans are climbing anyway, Shermans appearing on roads that shouldn't support tank traffic. A German defensive report captured 3 days later notes, enemy armour demonstrates unexpected climbing capability. Previous assumptions about American tank limitations appear incorrect. Defensive positions cited to exploit terrain advantages against armour are being directly assaulted by tanks that reach previously inaccessible approach routes. By October 30th, 1943, the 67th Armoured Regiment has advanced 12 miles up the coast. 81 tanks with modified clutches have operated continuously in mountainous terrain, 0 clutch failures. Compare that to the previous month. 27 clutch failures in similar operations with standard clutches. The modification's success rate is undeniable. Tanks with modified clutches are climbing grades that tanks with standard clutches cannot. The operational advantage is measurable. Units equipped with modified clutches advance faster, reach positions that were previously inaccessible to armour, support infantry assaults that would otherwise fail due to lack of tank support. By November 15th, 1943, every Sherman in the 1st Armoured Division has received the clutch modification, 214 tanks. 0 additional clutch failures reported in mountain operations. The statistics are compelling enough that other divisions request the modification. Army Ordnance hears about it in late November. A formal inquiry is initiated. Captain James Wright, an automotive engineer from the Ordnance Technical Division, arrives at the Naples depot on November 28th to investigate unauthorized equipment modifications. Wright is 32 years old, MIT mechanical engineering degree, 3 years working for General Motors before the war. He's accustomed to engineered solutions, properly tested, formally approved. The idea of mechanics riveting brake-lining material to clutch discs horrifies him from a professional standpoint. He summons Ray Sullivan to the depot headquarters. "Corporal Sullivan, you're accused of unauthorized modification of military equipment, specifically installing non-specification friction material in Sherman tank clutches. Do you understand how serious this is?" "Yes, sir." Clutch systems are precision-engineered components. The friction material is selected based on extensive testing to ensure proper engagement characteristics, heat resistance, and longevity. You cannot simply substitute random materials and expect acceptable performance. The brake lining material isn't random, sir. It's heat-resistant asbestos, same material used in Sherman brake systems. Heat resistance significantly exceeds organic friction material. But engagement characteristics are completely different. Brakes need maximum friction. Clutches need modulated friction. Using brake material in a clutch should result in harsh, grabbing engagement that makes the tank undrivable. Should, sir. But it doesn't. The modification has been installed in 214 tanks. All of them report normal clutch operation. Wright pulls out a folder containing field reports. "I've reviewed the maintenance logs. 0 clutch failures in modified tanks over the past 6 weeks. 0 failures in conditions that regularly destroyed standard clutches. That shouldn't be possible, your crude field modification." "With respect, sir, the results speak for themselves." "The results are impossible. According to proper engineering analysis, your modification should fail. The friction coefficient of brake lining material is wrong for clutch applications. The riveted attachment should create stress concentrations that cause material separation. The increased rotational mass should create engagement problems. Your modification violates multiple design principles." Ray meets his gaze steadily. "Sir, I don't know about design principles. I know that standard clutches burn out on steep climbs. I know that brake lining material handles heat better than organic friction material. I tested it. It worked. So, I made more. They all work." Wright sets down the folder. He's frustrated because the engineering analysis says one thing and the field results say another. As an engineer, he trusts analysis, but as a military officer, he has to trust results. "I'm required to conduct a formal evaluation. I'll need one of your modified clutches installed in a test vehicle. I'll run it through standardized performance testing at the proving ground." "Yes, sir." December 2nd, 1943. Naples Ordnance Proving Ground. Captain Wright supervises installation of a modified clutch in a test Sherman. The tank is instrumented with temperature sensors, torque measurement devices, and accelerometers. Wright plans to run a comprehensive evaluation. Engagement testing, temperature testing, endurance testing, failure mode analysis. The testing begins at 0800 hours. First test. Engagement characteristics. The driver operates the clutch through 50 engagement cycles. Fast starts, slow starts, hill starts, reverse starts. Wright monitors the instrumentation, recording pedal force, engagement point, torque transfer efficiency. The data surprises him. The modified clutch engages slightly more abruptly than a standard clutch, but within acceptable parameters. Pedal force is normal. Engagement point is consistent. Torque transfer efficiency is actually slightly better than standard specifications. The crude modification shouldn't perform this well, but it does. Second test. Temperature resistance. The driver runs the tank up a test slope at sustained high RPM in first gear. This replicates the conditions that destroy standard clutches. Wright monitors clutch temperature via thermocouple sensors installed in the pressure plate assembly. Temperature climbs rapidly, 600 degrees Fahrenheit, 700, 800, 900, 1000 degrees. This is where standard organic friction material begins to fail. But the modified clutch doesn't fail. Temperature stabilizes at 1100 degrees. The clutch continues transferring full torque without slippage. Wright checks his instruments twice, certain there's an error. There isn't. The brake lining material is handling temperatures that would completely destroy organic friction material. The modification is working exactly as Ray claimed. Third test. Endurance. Wright orders the driver to run the tank continuously for 4 hours, alternating between steep climbs and normal driving. This is an accelerated wear test designed to identify premature failure modes. After 4 hours, Wright inspects the clutch disc. The brake lining material shows normal wear patterns, no cracking, no delamination, no rivet failures. The modification is durable. Wright writes his report on December 3, 1943. The conclusions are straightforward, if professionally humbling. Modified clutch assembly, utilizing asbestos brake lining material, demonstrates superior heat resistance compared to standard organic friction clutch discs. Field testing and laboratory evaluation confirm reliable operation under conditions that cause standard clutch failure. Recommendation: approve field modification for continued use pending development of improved specification clutches. The report includes one additional paragraph that Wright adds after considerable thought. The Sullivan modification represents an example of practical field innovation addressing a critical operational deficiency. While the modification does not conform to standard engineering practices, its effectiveness in solving a life-threatening equipment limitation warrants official recognition and adoption. December 15, 1943. Army Ordnance issues Technical Bulletin TBORD 243. Field Expedient Clutch Modification for Mountain Operations. The bulletin officially authorizes the Sullivan modification, provides specifications for proper installation, and directs maintenance units to retrofit all Sherman tanks operating in mountainous terrain. Ray Sullivan's name appears in the technical bulletin as the modification's developer. It's the first time he's mentioned in any official Army document beyond routine personnel records. He doesn't see the technical bulletin until January. A copy arrives at the Naples depot. Mitchell shows it to him during a maintenance meeting. Ray reads the first page, sees his name, sets the bulletin down. They spelled my name right, at least. That's all you have to say? Army Ordnance just officially adopted your modification. Your clutch design is going into every Sherman in Italy, probably spreading to other theatres. It's not a design. It's brake lining material riveted to a clutch disc. It's a design that's saving lives. 14 men died from clutch-related rollback accidents in September and October. 0 deaths from clutch failures since your modification went into service. That's not nothing. Ray looks uncomfortable with the praise. He's a mechanic. He fixed a problem. That's what mechanics do. The recognition feels unnecessary, even inappropriate. Other men are fighting and dying in combat while he's getting credit for riveting some brake lining to metal discs. Sergeant Mitchell, can we just get back to work? We've got 6 tanks waiting for transmission overhauls, and the battalion wants them back by Monday. Mitchell recognizes the deflection but respects it. Some men need recognition. Others just need to do their work and know it matters. Ray is the latter. By January 1944, the modification has spread beyond Italy. Sherman tanks operating in mountainous terrain in North Africa, Greece, and later in France all receive the Sullivan clutch modification. The installation becomes standard maintenance procedure. When new Shermans arrive from the United States, one of the first modifications is replacing the standard clutch with a brake lining equipped version. Army Ordnance continues developing sintered metal clutches. The improved specification clutches enter production in March 1944, exactly on the timeline Ordnance originally projected. But by then, 8,000 Sherman tanks have already been retrofitted with the Sullivan modification. The field expedient has become the standard. Interestingly, when engineers test the new sintered metal clutches against Sullivan-modified clutches, they find minimal performance difference. Both handle high temperatures effectively. Both provide reliable operation on steep grades. The sintered metal clutches are slightly more durable, lasting perhaps 500 hours longer before requiring replacement, but the Sullivan modification, made from salvaged brake lining material and installed by mechanics in field depots, that performs nearly as well as the precision-engineered solution that cost millions of dollars and months of development to produce. The lesson isn't that engineering is unnecessary. It's that sometimes practical field solutions, developed by people who understand the problem intimately because they see it every day, can match or exceed formally engineered solutions. Ray Sullivan didn't have an engineering degree, but he had 22 years of experience working with friction materials, heat, and mechanical systems. He understood, at a practical level, what would work and what wouldn't. His hands-on knowledge was as valuable as any theoretical education. The German perspective provides additional context. Captured German technical intelligence reports from early 1944 note, with frustration that American tank mobility in mountainous terrain improved dramatically between October 1943 and January 1944. A report from the 15th Panzer Grenadier Division states, American Sherman tanks demonstrate climbing capability exceeding our calculations. Defensive positions sited on steep grades no longer provide expected protection against American armor. Enemy tanks reach positions we assessed as inaccessible to vehicles of that weight class. The Germans never determined the specific modification that improved Sherman climbing performance. Their intelligence, assessments speculated about more powerful engines, improved transmissions, or reduced combat loads. They didn't realize the change was something as simple as different friction material in the clutch. Production statistics tell the story of the modification's spread. Between December 1943 and June 1944, approximately 14,000 Sherman clutches were modified using the Sullivan method. Materials cost, approximately $12 per tank in salvaged brake lining material and rivets. Labor cost. Total program cost, less than $200,000. Benefit. Measurable reduction in mechanical failures. Improved tactical mobility, estimated 300 to 400 crew members who survived situations that would have killed them with standard clutches. The modification remained in service through the end of the war. Even after sintered metal clutches became available, many maintenance units continued, using the Sullivan modification because it was simpler, cheaper, and used readily available materials. In forward areas where supply lines were stretched thin, being able to manufacture clutch friction material from salvaged brake linings was a significant advantage. Post-war tank development incorporated the lessons learned. The M26 Pershing, America's heavy tank developed late in the war, used clutch systems designed explicitly to handle sustained high-torque, low-speed operation. The specifications emphasized heat resistance and climbing performance. Ray Sullivan's field modification had demonstrated that these characteristics were critical for combat operations, and post-war designers made them standard features rather than afterthoughts. The M46 pattern, developed in the late 1940s, featured a clutch system with twice the heat capacity of wartime Sherman clutches. The M47 and M48 pattern variants continued this emphasis on robust clutch design. By the 1950s, American tank designers had fully internalized the lesson. Clutch reliability is as important as firepower or armor protection. A tank that can't move is useless regardless of how well armed or well armored it is. Ray Sullivan remained in Italy through May 1945. He was promoted to sergeant in March 1944, primarily due to his clutch modification work. He declined further promotion opportunities, preferring to remain in a hands-on technical role rather than moving into supervisory positions. His final evaluation before discharge in December 1945 reads, Sergeant Sullivan has demonstrated exceptional technical competence and innovation. His field-developed clutch modification has been adopted across the theatre and significantly improved operational effectiveness. Recommend commendation for meritorious service. He received the Army Commendation Medal in a brief ceremony at the Naples depot in November 1945. The citation mentioned his technical contributions to improved vehicle reliability. Ray attended the ceremony, accepted the medal, thanked the presenting officer, and returned to the maintenance bay. He had 6 tanks waiting for transmission overhauls. After the war, Ray returned to Bakersfield, California. He went back to work as a traveling mechanic, servicing agricultural equipment across the San Joaquin Valley. He married in 1947, raised 3 children, never discussed his wartime service except in the vaguest terms. When his children asked what he did in the war, he'd say, "Fixed tanks." In 1968, a military historian researching Sherman tank modifications contacted Ray through Army records. The historian wanted to interview him about the clutch modification for a technical history of American armor development. Ray declined politely. It was just brake lining material. Any mechanic could have thought of it. Ray Sullivan died in 1982 at age 77. His obituary in the Bakersfield Californian identified him as a retired mechanic and World War II veteran. It mentioned no innovations, no modifications, no lives saved, just another veteran who came home and lived a quiet life. But in archives at the U.S. Army Tank Automotive Command, Technical Bulletin TBORD 243 still exists. The document that authorized field modification of Sherman clutches using brake lining material. The document that credits Ray Sullivan with developing a solution to a problem that Army ordnance couldn't solve quickly enough. The document that represents one mechanic's refusal to accept that crews had to die while engineers developed perfect solutions. Today, the U.S. Army Ordnance School includes the Sullivan clutch modification in its curriculum on field expedient repairs and battlefield innovation. The case study emphasizes several key lessons. First, practical hands-on experience can identify solutions that theoretical analysis might miss. Second, the simplest solution that works is often better than the perfect solution that takes too long to implement. Third, unauthorized innovation carries risks, but sometimes those risks are justified when lives are at stake. The plaque in the Fort Gregg Adams Ordnance Museum that mentions the Sullivan modification reads, "Field Expedient Clutch Modification, Italy 1943. Corporal Ray Sullivan, U.S. Army. Utilized salvaged brake lining material to improve clutch heat resistance in Sherman tanks operating in mountainous terrain. Modification adopted theater-wide, credited with significantly reducing mechanical failures and improving tactical mobility." The Germans had superior engineering. They designed the Panther and Tiger with climbing performance considered from the start. Their clutches were robust, over-engineered for extreme conditions. German tanks could climb steep grades because German engineers calculated every stress load and designed components to handle worst-case to perceptive scenarios. Americans had superior mechanics. They took tanks designed for mass production and efficiency, identified weaknesses through field experience, and improvised solutions using available materials. American tanks could climb steep grades because American mechanics wouldn't accept that the equipment they maintained was inadequate for the mission. Both approaches work, but in war, speed matters. The German approach required years of development and precision manufacturing. The American approach required a mechanic with brake lining material and a rivet gun. Ray Sullivan's modification was deployed in weeks, not years. That timing saved lives. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.